In this video, we're going to talk a little bit about what happens when magnetic fields change with time and how they create non-Coulombic electric fields. So we already talked a little bit about what happens when you move a bar magnet around physically. But in this video, what we're going to do is we're going to talk about how a current that changes with time can give rise to a magnetic field that changes with time, and therefore give us a non-Coulombic electric field that in principle will also change with time. And you might be wondering why we do this. This is actually a much more common example of the Faraday effect. It's not really common to have solid bar magnets and kind of moving them around, but rather that there are currents that change with time in some circuit or in some situation, and you have to worry about what's going on with regard to a non-Coulombic electric field. The two common examples that we have are turning on or off a circuit. So when you turn on or off that circuit, essentially you go from no current to some current after some amount of time. And then the second case is the case that's very common in your house, which is something that we'll refer to as alternating current. And we'll talk about that in another video. Or AC current. It's an AC signal. Okay. This is the kind of current that comes out of the wall in your house, and this is why we will analyze it. It's quite important. But for the purposes of this video, we'll focus on one. So in example one, what often happens is that if you look at a graph of the time versus current, when you switch on some sort of really simple circuit, there's an amount of time that it takes for the current to sort of hit what we would refer to as sort of the steady state current. Now that time can be really, really short. In most common sort of basic circuits, the amount of time for this to happen is micro to sort of nanoseconds. It's really, really quite short. And this model of the current looks like this mathematical function, which is a little complicated. So it's 1 minus e to the minus t over tau, where tau is the sort of turn-on time. Now, we're not going to analyze this one in detail because it's a little more mathematically complicated than we need. Instead, what we're going to do is simplify this model a bit and say that there's a rising time. There's an amount of time that the current rises, and then it's steady. And that rising will take to be linear and then flat. So instead, what we'll do is we'll model the current when a circuit is turned on in this way. And then when it's turned off, you can think of it as coming back down to zero. Okay? So using this, we'll be able to understand a little bit about what happens with regard to a non-Coulombic electric field. So the example that we're going to work with is an example that includes two loops of current. Now in the notes, those loops have a variety of turns, but in this video, we're going to just focus on having one turn for each. Okay? So the way that they're configured is that there's a big loop that looks like this. And it has a radius of, we'll call it RLG to signify that it's large. And inside, right at the center, there's a much smaller loop that has a radius that we will call RSM for R small. And the idea is that the areas of these two loops are given by ALG, which is pi RLG squared, and ASM, which is pi r sm squared. Now, the point of this exercise is what we're going to do is we're going to drive a current in the outer loop, and we're going to see what happens in the inner loop. Okay? So we'll drive a current around the outer loop, and we'll allow that current to change with time. Now, we've talked a little bit about what the magnetic field is associated with a loop of current, and that magnetic field that you're going to see right at the center is going to be mu naught times the current over 2 times the radius of the larger loop. Now, in this case, what we're doing is we're saying that that's the magnetic field that's associated with the loop, this larger outer loop, right at its center. Okay? Now, everywhere else, it's quite a bit different. But what we can do is we can approximate the very small loop as being quite small compared to the large loop, and that will allow us to make a statement about what is going on with the magnetic flux through that little loop. So by changing this current, we are, in a sense, driving a current in this smaller loop. So what we'll do is we'll calculate what the magnetic flux is through the smaller loop. And our definition of that is going to be this integral of the magnetic field due to the larger loop over that little piece of area. Now, if we assume that these two loops are flush with each other in the sense that the small loop is right inside the larger loop and they're in the same plane, then both B and dA, SM, are in the same direction. So we can approximate this as B, dA, SM, meaning that they're sort of aligned with each other. Additionally, if that loop is really small, if we assume that the loop is quite small, the little one, compared to the big one, we can assume that the magnetic field over the surface defined by that little loop is a constant. And so what that allows us to do is to both reduce this integral to this kind of calculation as well as to pull out the magnetic field and end up integrating all over the surface of that loop face. And so as a result, this magnetic flux, which does change with time because the magnetic field changes with time, is a result of just the product of the magnetic field, which changes with time, and the area of the smaller loop. So we can put all this together, and we can simplify this just a little bit. So what we'll have here is that this magnetic flux is going to be equal to mu naught times the current, which changes with time, over twice the radius of the large loop times the area of the smaller loop, which is going to be pi the radius of the small loop squared. So this guy is the magnetic flux that we expect to see at any given time when the current is changing in the outer loop. Now, this doesn't matter, actually it doesn't matter whether it's changing or not. This is actually what the flux is going to be. What matters is whether we see a potential difference, an induced potential difference around this inner loop. So that induced potential difference, we'll get rid of all this stuff over here because we've calculated everything that we need, is related to the time rate of change of the magnetic flux. So that induced potential difference, which is a non-coulombic potential, is related to the time derivative of the flux through the small loop. Now, if you look at this equation, all of these guys are constant except for this current. So this is actually a pretty general description of what happens in these situations where we have this small loop, namely that the induced potential is going to be equal to mu naught pi r small squared over 2r large squared. And the only thing that changes is that we're going to take the time derivative of the current. This is the only thing that depends on time. So this is a pretty general solution for this setup where we can assume that this ring is quite small compared to the outer one, where it's centered, and where it's flush with the face of the other one. So given all those assumptions, this is actually a very general result, and will work for any sort of current situation that we have, regardless of how it's changing. It's just how quickly is it changing. So for the case of a current that turns on, modeling it linearly, we'll say that there's some time constant, or some constant, some rate constant that tells us about how fast that current increases, right? So greater C, faster increase, lower C, smaller increase. So the time derivative of this is just a constant for a linear function. So in this sense, what we're going to have is that the induced voltage will be the same throughout the loop the whole time that the current is changing. That's very special. This is a special case for this specific situation where the current increases linearly with time. For all other situations, you're going to have a variety of potentials that will show up depending on what time it is. And for this case, it'll be just this very specific result. So what we've done in this video is talk a little bit about, what might happen when you have a magnetic field that changes with time as a result of a changing current, and how that can induce a potential around this smaller ring, and it will drive a current. In the next video, what we'll do is we'll talk a little bit about an actual practical approach for that, which is when you have a sinusoidally varying current, and then we'll actually graph that out and map it and see what actually happens in that situation.